Okay, so welcome everyone. Thanks you all for coming. Thanks thank you all the speakers and also the organizer and the sponsor of this workshop. So this workshop is entitled Workshop on Floating-Based Robots in Manufacturing and Logistic Operations, Opportunities and Challenge as a part of the International Conference on Humanoids 2020. So let me first introduce the program I planned for this workshop. I mean this is not a fixed program. I would like to be as flexible as possible. And so first, I will introduce more or less the topic. I will explain how the workshop is taking place, and then, let's say, in order, with 15 minutes for each of the speaker, we will just give a very short, let's say, summary of their talk that you probably already have seen online, because all of the talks are recorded, are online on our YouTube playlist. And in these 15 questions, 15 minutes, it will be just so this very short summary, and then just I will let's say state some open question or discussion topics to talk with the speakers. And also, if anyone in the audience or also the speakers have some topic they want to discuss about related to the talk, or let's say curiosities, anything, so feel completely free to interrupt at any moment and to ask any kind of question, and let's try to be as interactive as possible. So the outline, so in this slide, there are the outline goals of this workshop. So basically, this workshop regards the application of floating-based robots, like humanoids or mobile manipulators in manufacturing and logistic environments. Basically, these are the three questions that this workshop is trying to face regarding the challenges and opportunities, let's say, of this kind of technology in industrial environments. And the question that we are trying to answer, or maybe to talk about in this workshop, are so these three that are the main issues and challenges regarding the application. How should we let's say, tackle these challenges, and what are the benefits while solving these challenges? And also, one of let's say another point of this workshop is to inspire cross-discipline collaboration. As you will see later, we have talks, or maybe you already saw in the videos. We have talks related to control, to whole body controllers, impedance controller, to grippers for mobile manipulators, regarding related to learning, also some control theory. I mean, there are some really, let's say, cross-discipline talks, and in my opinion, this is a good point. So let's go forward. So the first talk is given by Dr. Johannes Ensberger from the German Aerospace Center, or the DLR, and this talk is entitled "Who Will Dare to Work Side by Side with a Potentially Exploding Robot?" And he's giving some thoughts and insights about truly robust and safe floating-based robot controllers. So I will just give some of the points he mentioned in his talk. So his talk is related to safe human-robot interaction, and he said that to achieve this safe human-robot interaction, one of the best approaches, or the best approach, is to use impedance controller, in which case we need torque control robots, in this case This talk is related to humanoid robots. And he proposed, as he said in the video, 3 beautiful simulation of the state-of-the-art controllers that are these 3. Inverse dynamics, passivity-based whole body controllers that he said that more robust than inverse dynamics, and modular passive tracking controllers, or MPTC, that are more generic because they can work both for fixed and floating based robots. And he also shows some simulation and real examples showing how these approaches work safely both for robot controlling and physical human-robot interaction. But after all of this, in the video, after explaining that all these impedance controllers are safe for the robot itself and also for the physical interaction with the human, he raised up this question, which is, are torque control robots safe? And he said, actually, no. So all of the things that he explained before are based on one assumption that he claims is the problem of this kind of controllers. So the problem is basically that the controllers assume that the contact point of the foot of the robot does not accelerate. And when this assumption is true, there is no problem. But when this assumption is, let's say, corrupt, like in the case of lifting up the robot, or when the robot steps into a hole, the robot explodes, as he shows in some simulations. And the source of this issue is that the whole body controllers are highly sensitive to assumption of contact constraints. So he proposed this new method, the relative center of mass to foot controller, RCF. And he showed some 2 simulations, one in MATLAB, both of them in MATLAB, one in 1D, in which we can see that the RCF is stable, and one in 3D that shows that in this case RCF is not stable, and also shows that MPTC shows, let's say, much less explosive behavior. Yeah. So the key of his talk is that making assumptions regarding contact constraints seems to be dangerous, and he, let's say, said these questions to all of us, which is, how could we solve the problem? So he also said that passivity-based controllers are better than inverse dynamics for human-robot interaction. But also these kind of controllers have the problem of designing stiffness and damping. One of the outcomes of this presentation is that Johannes says that before going to industry, robots have to be 100% safe. So based on this talk, there are, in my opinion, these discussion topics that, as I said, you can also give your point or ask your own question or whatever. So this first question is something is one question I will ask to all of these the speakers, which is, how far is this approach solution to be integrated in a real or conventional industrial application, and what challenges are to be solved? Another question could be, how could we solve the problem illustrated by Johannes? What are some, let's say, approaches on robust whole body controllers, safe whole body controllers, and safe physical human-robot interaction? So first of all, I would like to thank Johannes for his presentation. I would like to ask him if he wants to add something to this summary, to these topics. He wants to explain something he didn't comment in the videos.
Thanks so much, Juanma. Like, seriously, I couldn't have summarized the talk or these issues any better. Thanks so much. So, I clearly see that you watched the video in detail. That's really
Yeah, actually,
nice.
I really liked the video. It was very, very interesting.
Yeah, thanks very much. So let me just, maybe I can start answering some questions, and then or obviously in parallel people can try to answer questions or also ask questions. So how far is for example, our approach, actually we have several approaches. One is this like modular passive tracking control, MPTC. Then this recent one, like this relative center of mass to foot, RCF controls, which I presented at Humanoids actually. Then we, like I used to, like I visited Jerry Brett a few years back, like quite some years back, and got infected, like as from a perspective of DLR, I got infected by inverse dynamics. So I did a little bit, let's say a detour with regard to what my colleagues at DLR typically do, which is focus on impedance controls directly. So I went for inverse dynamics, also got to know that very well and gained some experience. So there's several controllers that I'm familiar with. And right now, so how far are our approaches or solutions to their integration in the real world, like regarding safety? Like, for example, we do demos. We did, actually, in this case, it was like position controls, but just to tell you, like how like pseudo confident we are with this technology, we had children standing next to the robot while it was active in position control. I mean, that's many years back, but we do have visitors, and any kind of visitors touch the robot, like even in in impedance control or in our whole body controllers. And what we do realize, like we personally, we know how, like where to push it and how strongly to push it. And like I was once asked on a trade fair, can I push the robot? And I said, yes, you can try. And the guy was like really lean, like he had watched some Boston Dynamics videos probably like a few days back. So he was leaning backwards and like pushing the robot 2 meters. And this was how confident he was about like the appearance of our robot. And obviously it, like, I mean, we had a crane, but so once again to say our approaches regarding actual safety for actual people, non-supervised and like without an emergency brake in the hand, we are far. And I personally believe that the really most critical issue is this one that I just pointed out here or spotted, which is like 4 free floating robots that are torque controlled. Like I think pure torque control or pure force control is anyway rather like stability critical. However, like impedance controls is meant to be better in a sense. It also has some notion of like a position error or like velocities and so on. So that's more of a behavior that's meant to be stable, and yet it turns out that the most critical point in my eyes are these contact constraint assumptions. So if you lift a robot, even if it's in a whole body impedance controller, so a controller that would like just fall over and like be perfectly passive, but if you introduce this this constraint or this assumption, the assumption on the constraint, and this constraint is violated in reality, the robot, even for, as I said, even for simple controllers, can become unstable. And before that hasn't been, as I said, before this hasn't been solved, I would not at all call this kind of robot safe. There's counter like other voices also amongst my colleagues who say, as long as it is detected, or for example, if we detect that the contact is broken or so, or if some velocity threshold is exceeded, we can just switch off and it's safe. But to me personally, I targeted one controller that is safe by itself, even if it remains continuously activated throughout any situation, hopefully. And to be honest, like the question, like preparing this talk helped me a lot to like figure out my thoughts and so. And I, like a few days after, I was like, now I might have the solution, and then I'm again not. Probably again not. So it's, I don't know, it's somewhere in the future, but I do believe that it exists very much, because like from what I can observe, humans and animals, when you lift them up, for example, or if they trip into a hole, they, like for example, tripping into a hole, yes, there's some, let's say, excessive velocities, but you don't explode like I personally believe it's still pretty controlled. And with this said, I like I leave the stage for other people asking questions and or maybe also answering.
Arashi has a question.
Yes,
Yes.
if I may.
Yeah.
I have one question or one comment, let's say. Thanks a lot, Johannes and Juanma, for the recap of this talk. Do you think the main problem is the nature of the control, that we have constraint-based, let's say, controller, or our inability to change constraints on the fly? So if we are able, through some, let's say, let's call it high-level techniques, to understand switch between constraints, update constraints, or switch off some constraints, I think we will not be able to see these behaviors. So I think our the gap between making humanoid robots, or in general any type of robot, to look intelligent, to avoid these kind of safety issues, or in general good performances, to achieve good performances, is not about, let's say, the control itself, because I think impedance controller they have amazing potential inverse or forward dynamics based approaches as well. I think that the main gap is how to define, for instance, the impedance control, as you mentioned, how to define these parameters, that comply with different scenarios. And in constraint-based whole body optimization techniques, how we define and revise these constraints on the fly, probably. What's your opinion about this?
So my personal, like, with some of my colleagues, as I said, like I'm continuously discussing, obviously, since I try to like advertise the idea of having this one all-time robust, no matter what controller. What did I want to say? Yeah, exactly. So my colleagues argue similar to you, as far as I understand. So basically, for example, there's no issues with having different controllers for different scenarios. For example, one controller for like a contacting scenario, and if you detect that, for example, the contact is breaking or it's different from what you expect, you just switch to another one. But personally, I think there's two things, like, or there's many things. I personally don't like switching. Switching always implies like either jumps or added complexity in order to make the jump, like to smooth out the jump. Then I believe there's issue regarding like detection of, for example, like you used to be in contact like a millisecond ago, but 10 milliseconds later, like you're losing contact, for example, and like how quickly would you detect? This detection is, to like, in my belief, it's kind of error prone. Like you might detect wrongly and then be maybe like even wronger. Switching controllers, like how fast would you allow to switch? You could have switching behaviors that are in a millisecond, or like, you see what I mean, like 2 millisecond frequency. So there's all kinds of like added complexity, and also kind of like a curse of permutations. So for example, if you have a 6-dimensional contact constraint that you're originally assuming, what about if just one of the axes, let's say there's like a rocker board that at some point it becomes a rocker board, you see what I mean? Or like you have some tilting around an edge, or this tilting around an edge becomes tilting around a point, or it's, I don't know, like it's, you see what I mean? Like there's all kinds of constraints, like permutations of possible constraints. Then there's like compliant grounds, which are anything in between, or you see, like it's all kinds, all kinds of different constraints that are the true ones. So personally, having like one kind of one controller per constraint, or also maybe if you have a constraint, like a constraint detector, or like a constraint observer, and then have one generic formulation for this detected constraint, like to handle the situation, that would be fine. But observers typically have a delay anyway. So that's why I'm hoping to have just one controller that would work. For example, both when you like lift the robot up, like for example, like imagine a cat or a dog or any animal, you lift it up. Maybe they do some stretching. Maybe they react in order to like not stretch. But I think if you just quickly lift them up, they would maybe stretch a little bit. But then you put it back on the floor and it would continue walking or continue standing. And well, like to me, this scenario of lifting a robot it happened to me at least once, at least once, to have switched on the whole body controller when the robot was in the air, like in mid-air. It was just trying to like produce those 76 kilos, or I don't know, 50 kilos, what it was back then. And like obviously there was some safety measure kicking in after I don't know, maybe 100 milliseconds or so. But there may exist research platforms or even whatever platforms that do not have safety measures. So I asked around in my community, let's say, like internationally, and I heard of, I believe, 3 other cases, or like 3 other researchers said, yes, definitely, if you lift it up, it explodes. And one even told about another like demo during which they believed the robot was offended, and they did not have any software emergency off, so it was really tough to catch the robot like when exploding. So yes, I believe it's tough in a sense. I've been thinking about it for, I don't know, quite some time, like several years, and still didn't find a proper solution. But I hope that this relative center of mass to foot controls, that this will help. For example, with when you're falling down, and if you don't care about absolute positions, but rather about relative positions, that should help. At least these simple simulations, they give a hint that this very much helps. On the other hand side, when like some of the stuff that I said in the video, I really just learned by doing the video. I was about to say, yeah, and now you see this one explodes the most. But for example, that this even absolutely formulated, that this MPTC controls was performing better than the relative in this example. Yeah, exactly. This showed to me that like this RCF controller, the meant to be more stable, this one did work with the assumption that the foot is not accelerating still, right? And this assumption made the whole body controller explode like really badly, very much comparable to inverse dynamics. This other absolute formulation, it was really, really surprising to me. So it did not explode so heavily. It has no assumption on the foot acceleration. That's my church over there. Sorry.
Right.
So there was no assumption on the foot acceleration. However, there was an assumption basically on thrusters in the foot. So there were completely wrong assumptions about the contact wrenches. However, to me, like my personal takeaway, and I hope to like deepen that in my future research, it's probably better to make wrong assumptions about contact wrenches as compared to wrong assumptions about contact constraints. And I think that what might be the link, or the key insight is that making assumptions on the constraint, you make assumptions also assumptions about what the what the joint torques have for an effect on the contact wrench, rather than having kind of an like open loop wrongness in the like how wrong is the assumption on the contact wrench, even if it's in the like in this absolute MPTC formulation, even it's like a thruster that is not there. So as I said also in the video, this absolute MPTC is very much imperfect, having these like virtual and non-existing, so wrong thrusters or assumptions on thrusters, and yet it looks like this wrongness, like assuming wrong contacts, has a more drastic effect.
So yes, thanks. I think Jay has a question or a comment, but just to conclude what I wanted to say, I think it's a little bit like we call collaborative robots that have a payload below a certain kilograms, right? But our definition is because of our lack of being able to control robots even with 1 ton of, let's say, payload, or hundreds of kilograms of payload, in a way that they can behave collaborative, you know. This is our lack of being able to make, let's say, these KUKA giant robots or ABB giant robots to perceive environments and act safety around them. That's why since we are not able to perform that, we're saying that, okay, those are not collaborative. The ones below 1 kilogram, 10 kilograms, 16 kilograms, whatever, with the certain shape are collaborative. I think also here, you know, it's the definition that we are setting is because of the limitations provided by the way we control at the moment the robots. And as you mentioned, I think there's a lot of work to be done on sensory perception of the systems, processing them, and trying to be able to really revise constraints. Or it's a little bit. I look at all the controllers that we are developing, even the ones that with a certain level of generality, but it is somehow very close to point-to-point trajectory planning, because sometimes by imposing these constraints, we know what the robot is supposed to do, you know, so you impose constraints. So it's some sort of expected behaviors that we code on the robots, and then when it does it, we are super excited that it did it. But so we probably need to really also, you know, relax those. I mean, go find some methods that the robots can maybe rationalize and define the constraints based on the perception data that we have. It's really tough to do. Of course, there's a lot of like reinforcement learning and things that are happening still. The research is very limited. But I think, as you also mentioned, it is quite nice to relax part of these constraints, but of course not around people. You know, trying to understand how we can adaptively define these constraints or switch in between. Not switch. It doesn't mean that turning one off, or like smooth transitions between constraints could be quite helpful. Jae-Hyung, are you still willing to ask your question, because you lowered your hand, I think?
Yeah, because I think we don't have that much time, but I want to make it quick. So I really enjoyed your presentation, Johannes, and I really 100% agree with the comments you have about the whole body control, especially with the torque control approach, right? So recently, I have many experience with working with position control robot, and I feel very safe. Much comfortable. Yeah, I feel much like relaxed near the robot. So these days, maybe I should switch to work on the position control robot. This is my opinion. Anyway, if we think about this bipedal locomotion, so this is another topic. And it's not related to whole body control, right? So if we solved all the problems with whole body control and torque control, still we have the issue with the bipedal locomotion, because this is another level of the safety. So what do you think about it? Because DLR has this nice humanoid robot. Someday this will be much better than mobile manipulator, like field mobile manipulator, or not? In near future, or this is still far away? What do you think?
I think that very, very much depends on like the requirements of the task. In many applications, like wheels are just easier, maybe cheaper. Also regarding like the natural stability, like people are just glad and like relaxed about something that's never gonna fall over, right? For humanoid robots, I personally see humanoid and other legged robots, but like especially humanoids, I would call them as a very, very generic tool in order to probably like replace people in places where people cannot go, like let's say for firefighting or disaster relief or similar. Yeah, so I think in many applications, like a wheeled solution will do, like in many industrial settings. However, there's maybe there's not only industrial settings, but also like settings where let's say the physical use is not so important as compared to the appearance. So if you want to, for example, have a Disney character walking around, it's obvious that it's nicer when it's like moving on its legs. Yeah, there's really like I would believe still quite some scenarios which make humanoid robots or bipedal robots a good solution, right? Then there's for example, if it's regarding really like rough terrain or like very confined passages or stuff that's made for humans, or if the robot is controlled by a human, it's sometimes more intuitive to like control a humanoid as compared to some mobile six-armed monster, right? Yeah, I'm not quite sure if I answered your question.
Thanks.
That's fine. Thanks for your comments. And I'd say let's move on to the next speakers.
Yeah, okay. I
And
think
thanks for the time and sorry for being so long.
don't worry. So in any case, if someone else has any question, maybe at the end of the workshop we still have some time. Of course, I think that all of the speakers are 100% sure to answer any kind of question. Also, if you want to contact them via email, wherever, they of course will be super happy to answer your question. So thank you, Hannes. Let's move to the next talk. So the next talk is was presented by Jen Park from the Seoul National University, and is he's also one of the co-organizers of the workshop. And the title of the talk was "Difficulties in Assembly Tasks for Floating-Based Robots." So in his talk, basically he presents this project that consists of assembling a chair from instruction in figures. So basically, one of the let's say challenge was to recognize instruction and to find the relations between different parts. And so he also presented different approaches that was done from other university and also his university that are all of them based on fixed base robots. So basically these approaches are the one in one of them they use the two universal robot UR10, another one used two universal robots UR5 with a moving table. Another one used three RB5 with a high D of robotic hands, and the fourth one, which is the approach they followed, is using three Franca Panda, three Franca Mica Panda, and motion planning, complex motion planning actually for handing over. So in the presented approach, they use torque control robot without hand-eye camera. So they present also their approach on complex motion to deal with uncertainties for pecking hold task, constrained motion planning for multiple robots, and also they presented some fault tolerance, let's say some recovery strategies. So all of these works related to assembly from instructions were based on fixed-base robots. So at the end of his talk, he let's say stated these 2 points in regarding what are the benefits and the challenges of using floating-based robots. So according to him, the benefits of using floating-based robots are that they have a larger workspace. Then for this kind of application, we will need less number of robots and regrasping, and there will be more redundancy on the system. On the other hand, the challenges of using this kind of robots will be that the number of uncertainties will be increased. So probably we will need some precise localization and visual servoing. The calibration, which is another point he explained on the talk that was already challenging for the fixed base robot, will be even more challenging. It will also probably require very high complex motion planning regarding to high D of robots and model uncertainties. So from this talk, I would like to let's say express these discussion topics, all of them based on my own. So again, if any one of the audience have some other questions, topic they want to discuss, some curiosities, please be completely free to ask. So again, the first question that I am asking to all of the speakers is how far is this approach solution to be integrated in a real or commercial industrial application, and what challenges are to be solved. Also, other points or the discussion points is that what are the strategies for on assembly for floating-based robots? What are the challenges of using this kind of robots in an assembly task, which some of them were already stated by the speaker? What are the challenges and benefits of using multiple robot motion planning? Let's say. So, John, if you want to add something to this talk of, I mean, to my comments, or if there are any question from the audience, whatever. So please be free to talk.
Okay, so there is a question.
Yes. Hello. Yeah. Thank you for your presentation. I have one question about the application for pegging hole. What is the clearance that you implemented for the assembly? And I just couldn't see the control equation that you presented. You were saying in the presentation that is a compliant control, but just to make sure I couldn't understand. That's why I wanted to ask what type of controller you used for that application.
Okay, so for clearance, this is the IKEA Stefan chair. So you can think about that. So there are pins and the furniture part. And I think so clearance, actually, it varies. There was a big problem. Sometimes it was very easy to enter. Sometimes it was very difficult to do it. It was there's no clearance sometimes, and there's like, I think at least 1 millimeter clearance. So it depends, and it's wood. So if you do it multiple times, it becomes bigger hole. So actually, when we practice, we had to buy a lot of Stefan chairs. So I think we still have a lot, probably like more than 20. And for control, what we have done was pretty much standard operation space control approach. So I don't think there was not much additional controller. Yeah. So it was torque controlled robot. So proposed operation space dynamics, lambda x plus mu plus p equals f, and then compute f, and then transform it to torque by Jacobian transpose. Okay. So,
thank you for your answer.
Yeah. Dong-hee, you have a question?
Yeah, sure. So thank you very much for the really nice application. It was interesting to see your work. So I have several questions. I don't know where to start, but maybe let's start with the first one. So maybe you're mentioning about you deal with this, the not correct automatic things with the calibration. So if you have a hand-eye camera, then the problem will be easily solved.
Yes, I think so. Yeah, and that's the strategy that the other team took. For us, we thought at the beginning, I think our information was good enough at the beginning, so we didn't install hand-eye camera at all. And then later, we figured that this is not enough, and then we were too late. We couldn't change hardware, so we had to just deal with our hardware. So the main problem was that the pin is very small. So small pin were about 5 millimeter, and hole is also 5 millimeter, and the hole has very small part. So if you have a wrong calibration, then you just miss the part. So you can never be close to the hole. So if you imagine this infinite plate with a hole, then you can do it with a large error. But the error tolerance was very small. So that was the main problem for us.
Okay. So you deal with especially difficulties because you have many assembling points, right? And then it has to go into the simultaneously, more or less, in reality. So what would you say, what would be the really now your point now after you did all the experiments and then you did all this, would you change some of your strategy? What would be the most difficult way or difficult part was how would you solve this multiple location assembly point more efficiently?
So many questions. This
Yeah,
is
yeah.
very
I have one more even.
So I didn't have time to explain all the strategies from other teams. So clearly the hand-eye camera is very useful. So without it, I don't think it's possible. So we need the camera, obviously. And another thing was that we used only simple grippers. So that was the mistake, basically. So whenever you want to manipulate some object, you have to move the arm totally, right? And when you do that, you lose accuracy because you have to move a lot, right? But if you use a gripper or hand, then you can do fine motion with very small motors. That can, I think, help a lot. So I think for fine manipulation, you need to have some robotic hand. And then for large motion, you can have manipulator. Then I think this is a very good combination. So another team had this strategy, and that was very, very effective. So I think this is very similar to going to mobile manipulation. So very fine manipulation, hand, and another level will be arm, and then another far bigger level must be a mobile platform. Then we have like 3 steps. Then I think we can have a better strategy to deal with assembly or manipulation tasks. That's my like rough idea. Yeah.
Thank you. Maybe if other people have questions, I would let other people to ask first. If not, then I might ask one more. So how did you deal with the task planning and motion planning together before your controller?
Yeah, so that's the most difficult part, I think, in general. So task planning was done by other university. So this project was a combined project with AI and robot technology. So another team, the GIST, read, I mean, recognized these figures and then made the instruction for us. So they made a task planning, and then given task planning, we did only motion planning. However, sometimes we had to choose where to grasp. That was the most difficult part. So for some easy tasks, we automated, but some very difficult parts we didn't automate. We couldn't automate, so we had to do manual selection. So there was kind of cheat in the middle. Yeah. So for example, when we rotate the whole the chair with 3 arms together, this was really, really like constrained motion planning. And whenever we try, it failed. We couldn't make motion planning. So we had to choose where to grasp by our intuition. And I think probably this is because we are not the motion planning group. So we are not specialized with the constrained motion planning. We read papers about motion planning and implemented in a very short time because the total project time was about 18 months. So we didn't have that much time. So we tried as much as we can, and that was the problem. But for grasping some part and moving to another place, when we do that, we automated this process. So we chose optimize grasping point and then move it to another point. And another thing that I want to mention is that when we move part, we use the joint space control approach with joint space motion planning. I think that was much more efficient than everything doing in task planning, I mean task level, because it was difficult to avoid obstacles if you do everything in task level. So when we do peg-and-hold motion, we did it in task level, but for other motions, especially for moving parts, we did joint space planning and control. That was quite efficient for us. So I think mixing controllers or planning approaches is, I think, necessary for some tasks.
Thank you.
Thank you for good questions.
Okay, so if I don't know if there are more questions.
There's just one question, if I can ask.
Okay.
Do we have time? Or one
Yeah,
more
yes,
question?
yes, yes.
So I want to actually ask the question. I mean, your comment against yourself. You know, they say what you say will be used against. So you said that you're more happy recently to use position controlled robots. And I was wondering. So now in these kind of scenarios, how would you want the robot to behave with a position controlled? You know, of course, this is a very challenging and traditional question. But of course, from one side, you mentioned that this, from safety aspects, of course, position controlled robots would be great. But can we do these kind of interaction tasks or interaction planning tasks like such constraint situations with a position controlled robot? Of course, admittance control is a way to go, but of course we know all about the limitations of the admittance control as well.
Yeah. So I think if we I think the definition of position control is a little bit difficult to define in some way. So, for example, if we have like a manipulator with motor and gear, which can be back drivable without the torque sensor, then is it a torque control robot or position control robot? It's a little bit difficult to define, right? So if we have a robot that can be a little bit back drivable, then we can use joint space control with lowering gains. Then I think it can be very similar to torque controlled robot. I mean, torque controlled approach, because this is quite in between torque control robot and position control robot. I think that can be very effective without, if we don't want to use force torque sensors. So if we use force torque sensors, then we can make it very stiff and then interactive. That's possible. But if we don't want to use the force torque sensors and try to make it inherently safe, then I think we can try to lower gains or gain scheduling. Sometimes we can make it low gains and then sometimes use high gains, then we can switch or transition between two modes. I think that's really possible, in my opinion, and feel much more safe in general.
Sure, of course, I agree with that. Right, thank you.
Okay, thanks a lot, John. So I think if maybe we can move to the next speaker. So again, thanks. A very interesting talk, a very interesting discussion. So the next speaker is Concha Monge from the Carlos III University of Madrid. Her talk is the title of her talk is Fractional Order Control of Soft Robotics Links. So in her talk, she presents a soft link for any kind of robot, but applied mainly for the neck of let's say humanoid robots. And she said that one of the problems of soft robotics is modeling, because it's very hard to model. So the proposed solution is to use fractional order controllers to deal with a model. So there is a typo here. This is model actually, with model simplifications. So in their approach, they use a simple model with under this assumption, which is that the stiffness is isotropic and linear elastic. They use inelastic tendons. There are no dynamic effects on the beam, and there is the constant curvature of the beam. I don't know why it's not okay. They propose two control perspectives, which are encoder-based control and IMU-based control. So they propose a robust control, let's say, strategy, and the uncertainty sources are that the masses at the tip of the soft link may be different, and the distribution of the force and velocity depends on the position of the pulley. So they developed these fractional PD and PI controllers, and she shows some simulation and experimental results for a soft neck for a humanoid robot. Based on their results, the IMU-based control outperforms encoder-based control. She also presents their work in progress on a soft robotic arm. Also, the possibility to replace the tendons with soft actuators. In this case, she proposed using shape memory alloy actuators. This kind of actuator, as she explained, bends with the changes of the temperature. And she also presents some future works, which is this origami-based robot that you can see here. So from this talk, I selected these discussion topics. Also, as I said before, if someone wants to ask or add something, feel completely free. So these discussion topics I selected based on the talk was, again, the same question for all the speakers. How far is this approach to be integrated in a real industrial application, and what challenges are yet to be solved? And other discussion topics are the soft robotic modeling, like strategies use complex or simple model. What strategies are for soft robotic control? What about using soft actuation, like the actuators they propose in Concha proposing in her talk? This is more like a personal question, which is how to scale up this soft robotics to be integrated in, let's say, practical manipulators. So thank you, Concha, if you want to add something or if there are any questions.
Well, thank you very much, Juan Manuel, and all the organizers for inviting me. It's my pleasure to be here sharing this research. I would say we are starting because this is a proof of concept, right? But we are quite happy with the first results. And in fact, this proposal is under a patenting process with an enterprise, international enterprise. We are working together on industrial thesis to apply these to real robots. And I agree, this is in a very first stage of development. But hopefully, let's see what future comes. Right? But we will be able to see these implemented in real manipulator robots. As you have seen, here the idea is to introduce in a real robot, to introduce soft links and see how they behave with the soft links, right? Why soft links? Well, mainly because safety is one of the issues, right? Because hitting with the soft robots is less dangerous than if you do that with a rigid robot, of course, right? So safety is for sure one of the reasons why. But of course, the type of movements you can achieve, the range, the working space you can reach with soft links is different, right? And more versatile, I would say, right? So there are a lot of advantages when using soft elements in robots, right? So the idea was to, first of all, develop the link itself, proposing different architectures, morphologies, materials, just play with the materials and designs, right? And then later, of course, to model that particular design, and of course we were aware that modeling these type of links is quite challenging because of the nonlinearities and mismatches are always there when you model and simplify the model. But the thing was later, okay, let's face these as a simple model, and let's these problems of just simplifying the model that much, right? Designing controllers, because my expertise comes mainly, or is mainly, control, right? Fractional order control, which is a specific type of controllers I will introduce very briefly in 1 minute. So the thing is that, okay, I definitely need to develop a type of control, architecture, right, which is able to face or to deal with all the uncertainties I have in my model, right? So so this proposal faces differently the model design, or the design of the link, and also the control of the link, right? So what we do here is to, okay, let's act with simple motors, right? we have motors acting in a position controlled way, right? Changing the tendons lengths and then moving the platform, as you have seen in the videos, right? And this is our first approach, and the tendons are totally inelastic. And then why not to improve the softness of the system, introducing elastic tendons, right? Not just the link itself, but also the tendons, right? And for that we use shape memory alloy actuation, right? So we have faced these two types of models or designs, and the main thing here is to to design the controllers, right? And we want them to be very robust. Why robust? First of all, because we have model uncertainties, of course, and also we are using rapid prototyping, so it means that sometimes the pulleys are not exactly well located, and it changes the model a little bit, and so on. So we want we want something to be robust to all these stuff, right? So what we are doing here is to propose a type of fractional, a type of controllers are fractional order controllers. So it is, maybe it seems like difficult, but it is not at all. The thing is that you have the simple current ideal PID controller, everybody knows about it, but let's generalize the derivative and the integral actions of those type of controllers, right? And make them fractional, not just first derivative, first integral, but of order 0.8. Why not, right? So there is a theory behind, but the fact, to very simplify this, is that instead of having 3 parameters, proportional, derivative, and integral gains, now 5, because I introduced the order of the integration and the order of the derivation. So with 5 parameters, and very graphical and simple to use tuning methods for these type of controllers, I can guarantee the robustness that I want. So finally, what we have reached is a control architecture guaranteeing that different masses on the tip, right, acting as a neck, as a approach, are totally able to be controlled in a very robust way. The overshoot, the isodamping property of the system is guaranteed. And of course, those mismatches coming from rapid prototyping are also solved somehow, right? And then the following step is to use it not just as a simple neck, but as an arm. This is the challenge, so that we can manipulate loads. And so we have modified the design a little bit. And apart from that, we have tested with different loads, and we have seen that the system is keeps its robustness, right? So we are working mainly on these issues, redesigning, not only the design itself, but also the controllers we are using, and proposing these kind of strategies, allowing us to simplify the models deeply. When it comes to soft robotics, this is important, and then later to face the simplification with the control part, right? So if you ask me, how far are we from implementing these in a real application? We are far right now, because there are many things to be done. Juan Manuel, you asked me about scaling the system, right? So of course, it is simple. We can scale these, but of course, and in fact, this is quite big already to be able to deal with a reasonable amount of loads, right? But it is our main purpose not to make it bigger, but maybe smaller, and not acting just as an arm, but maybe as fingers in a hand, right? So we are, of course, this is a challenge. We have a new project that we got it 2 weeks ago. So we are scaling the system, of course, and checking all the possibilities. But I repeat, we are far from being in a commercial stage, even if there is an enterprise interested in this. So, well, this is a brief summary. and I'm very happy to ask and to solve any questions you may have about this. Thank you very much.
Okay, thank you for your answer. So if there are any question.
I would have a quick question. This not being ready for application, is this regarding the controls or just the hardware? Like
Well, I would say it is more related to the material itself.
Yeah.
I would say, right? Because of course the material you can prototype the material with different densities and dimensioning the tendons and the torques and forces on the structure and so on. But still a lot of research have to be done in that part. We are not that expert on materials, so we are working a lot on that and with other partners coming to help us on this, because the control part is quite controlled, right? But we have to still to improve the design, I would say, with new materials, more softer actuations, right? And this is for us the main part. Even we are thinking of why not self-healing materials. As you know, this is a very innovative and interesting, challenging thing to study. But we want the materials to be so soft that we could even repair the material, applying heat sources, or there are many. It depends on the material, but different strategies so that the material can heal itself. And for particular applications, we can have a self-healing design, which is another of the points we would like to address in the future. So materials are for us the challenge.
Yeah. Thanks a lot.
You're welcome.
If I may ask a question, by the way, there are some questions in the audience by raised hands. Juanma, maybe you can have a look at the list. So very nice presentation, thanks, quite inspiring. My only question to you was, how do you think this complexity, maybe, oh yeah, you're sharing the screen, right? So I can take care of that, don't worry about it. Yes.
No, actually I discovered how I can have a look at it.
Right. So my question is this, sorry, how this complexity scales with the required high payload, when you, for instance, are about to put these robots in industrial applications, you need to cover a wide range of payload. So usually in soft robots, one of the issues, of course, the accuracy is one big challenge, but to increase the payload, to have a human compatible, let's say, length and volume, let's say, we cannot really scale the actuators, these soft links larger. We need to use multiple of these actuators, and then actually this can bring a lot of complexity in control as well. So have you had any experience in seeing how this complexity scales up? Like it arrives to a point and you say, okay, for the time being, maybe it's not, we don't have tools to deal with it, because anyways PID control has its, we are for such a nonlinear system can cause problems. I wanted to have your opinion on this.
Yes, I totally agree with you, Arash. You're totally right. Of course, it is not that simple scaling these, because you can put more links together. In fact, we are doing that, and but the problem, scales very rapidly. So, but we are confident that with a strong design of just one simple link, right? And with the appropriate material, that's why material is very important here, we could face all these. So we don't want to be in need of coupling a lot of links to do the task, but to have the material ready, so that we can guarantee that with the minimum number of links all together connected, we can face the problem, right? So that's why we are working a lot on the design, on the material, on the compressibility of the material, because another way of being able to support more loads, a heavier load, why not to compact, to make it more compact in a compression way so that it can face higher loads, just the same link. Right, so of course this is difficult. The model is more complex when you connect different links. We are in fact now working with 4 of them connected, and of course the kinematics, dynamics of that is difficult. Even if so, the controllers seem to be working correctly. We have to adjust, but we are in this phase right now. So I agree this is difficult. We will try to minimize the number of links to be connected so that we can just with 1-2 links to be able to face the problem, scaling the material, scaling the dimensions, scaling the density. But we of course, this is maybe I don't have the answer, but we are working on that. And of course, this is the main problem we may have. Mm-hmm.
Okay. Yes, of course. Thank you. Thank you very much.
Thank you, Arash.
Okay, so I think there's another question from Daniel Riksen. So probably it's going to be the last question, and then we can go to the next one because we are running a little bit of time.
Okay.
Thank you. Can you hear me?
Yes, perfectly well.
Thanks for your nice presentation. Dan Riksen here from the TU Munich. This topic of soft robotics is really interesting, and many people try to avoid having good models. As you're saying, it's difficult. But how much could you really gain by having good models? Because doing also a little bit of structural dynamics, there are a lot of tools in, say, the structural dynamics community to have very accurate models that are very fast using some special reduction techniques. I mean, how much would that really help to have good dynamic models for your controller, which you usually try to avoid?
Yeah, well, very good question. I agree. I totally agree. We could have used a more complex and accurate model than the model we use for that. But the purpose we had, the approach we wanted to face was to test the robustness of our controllers. That was the main reason why not to consider a more complex model that we use for other purposes, right? But for this purpose, we wanted first to see if our controllers can adapt, can face the particular main, I would say, mismatches that we have to face when simplifying the design that we reached, right? So, so I agree that when I say the controller is robust, it is not robust to all type of mismatches and non-linearities we have neglected, of course not. But we have identified the main, in our design, the main parts that are very sensitive to variations. For instance, the mass at the tip is affecting the model strongly, right? But we have identified the parameter in the transfer function or in the model mainly affected by this change. So we have designed the controller to be robust to that particular change, that particular parameter. Of course, in a different design or changing other things, not just the mass, but maybe, I don't know, the density of the course. So, but in our case, for our application, what we decided was to, okay, let's assume that we are simplifying this, even if we could consider a more complex system, model, of course, and let's see how the controllers behave. Because the control part was an important issue. Now, it is the design, the main part for us, and the model, and we are improving that part.
Okay, thanks.
Thanks a lot for your question.
Okay, so thank you, Concha. Thank you very much. Very interesting talk. So let's move to the next one. Also, a reminder to everyone, if you want to add some question, maybe at the end we can have some time of. I'm 100% sure that all the speakers will be more than happy to answer all your questions if you want to contact them via email, whatever. So feel free. So let's go to the next one. So the next talk was done by Professor Dongyi Li from the Technical University of Munich. And the title of the talk is Collaborative Robot Programming for Manufacturing. So in this talk, she raises up how robot learning could enhance robot programming for manufacturing. And so she basically shows four, let's say, strategies. So the first one is the robotic learning by kinesthetic teaching. So she said that this kind of, let's say, strategy is the use of the pose memory, which is not, you cannot generalize. Then the use of trajectory learning includes more generalization, and in the end, the use of online refinement includes some impedance behavior and incremental learning and direct teaching. One of the main problems stated for this kind of strategy is that it can only be used for one task. So trying to solve this problem, she also showed another approach, which is the use of these learning strategies for multiple tasks. In this one, they prioritized the task. As an example, she showed one robot one application in which the M effector tracking has a high priority, and then the land space has a lower priority. Another word she presented is the use of, let's say, the application to conditional task. In this case, it requires conditional reasoning. It requires also to cluster the trajectories, and then to monitoring or replanning based on this learn. And there are, she also showed in the video a couple of examples to replan, to learn how to replan based on the weight of the object that the robot is grasping, and also a multi-class sorting experiment, which is the one that we can see now in the video. The last approach she presented is called continual learning. This one requires to detect the anomaly. In this case, this approach, if in the case that the robot detects one anomaly, has to report to the human user. Then the human user teaches the robot, trying to teach how it should behave in the case of this anomaly repeats in further cases. Yeah, one of the statements of this talk is that the collaborative incremental robot programming leads to achieve hierarchical and conditional tasks. So from this talk, again, there is the same question that I am doing for all the speakers, which is how far is this approach for integrating it in a real industrial application, and what the challenges are to be solved. Apart from this, there are other question or discussion topics, which are how to explode these approaches for floating-based robots, as in the case of local manipulation cases. Some other points to discuss about are the learning strategies for robot programming. What skills has the robot to have or to learn, like multitasking, conditional task, continual learning, or let's say fault tolerance. One other question that probably we can take this at the end when I present my own talk is about teaching interface, because as you will see, we are using also some kind of interfaces for let's say conjoint human robot action. So probably I will retake this question at the end to give more time to you. So again, if someone has any question, also Dongi, if you want to add something on this, please go ahead.
Yeah, so thank you very much for the nice summary. Yeah, so let's see if we have any questions coming.
Yeah, actually, there are some questions on the chat. So if you want, I can read. So Francesco Judic is asking, hello, Dongi. Thank you for your demonstration. I really enjoyed it. I have two questions. So first one is in multi-class sorting without vision. What type of hierarchical clustering did you use? I mean, did you use a single linkage, complete linkage, or other kind of linkage? And a second question is, assuming you have a large amount of demonstration data, could this approach be computationally demanding?
Okay, yeah, so thank you. Actually, maybe I would answer the second question. So actually, learning from demonstration usually does not require so many demonstrations. So probably you saw this sorting demonstration cases, right? Even with sorted like full milk box or empty milk box, we just showed like 2 examples or 3 examples of each classes. So it doesn't really require that many of the samples to learn. So usually it is a much more data efficient. And the way you use the kinesthetic teaching, of course, if you fully use the human's kinesthetic teaching data, then there might be a bit influenced by the human force. So maybe the value you observe might be not 100% accurate. So sometimes it is good to mix with human demonstration together with robot generates the shown the behavior once without the human's forced insight, so that you might have a bit better sensory data, right? Because also when you learn some new sports, you cannot really learn what is really correct proprioceptive sensor values are when human teacher continuously touching your limb, right? So first they show nicely, but then once you try successfully the task with your own body is very important to learn quickly, and that would reduce a lot of samples you require for the learning. And about the clustering, we do not do at the moment this the sorting example, we do not do the hierarchical clustering. So it is only about really using the how shall we say, just to come up with a very simple unsupervised clustering approaches. But of course, if you see a lot of different examples of the skills, then there might be coming up some hierarchical clustering. So which works, we did it about the one paper we did together with Dana Coolidge around in 2012 at the IJRR. Then you made it required a lot of skills are inside, then you would come up with the clusterings. So once you have, you start with a completely zero knowledge. So you clustered, different things, close things together. And then within that same cluster, you see some kind of, again, another subgroups are building up, then you make another subgroups. So in this way, you can also make hierarchical clustering. But simple example like what we show in the presentation today, in that presentation video is a 2-class clustering, a 3-class clustering. We do not need to do so much hierarchical clustering. So I hope that answered to the Francesco's questions.
Okay. Are there more questions?
Maybe I might, okay. Someone that tries to answer some of the questions you raised here. It is, of course, maybe I would try to say second question, how this, the robot learning approach for the robot programming would fit for the floating-based robot, right? It is a very hard problem. In fact, I showed one slide there, how we teach the the DRR humanoid robot Toro to do the bimanual lifting task. At that time, we did the kinetic teaching, direct teaching, basically. Then the difficulty part is, of course, human force exerting affects robot's balancing stability. So we have to take care of additionally, because the human user shouldn't take care of, afraid of giving the disturbance to the robot, and then he cannot really show the task properly, right? The task human want to show the robot was a manipulation task, but robot has to deal with, underlying balance problem itself. So how we did was we combined with a momentum-based disturbance observer, and then we tried to compensate that disturbance by the predictive balancing control algorithms. So this way we did it. And then I think free floating based robots, and then doing it with the kinetic teaching, we should consider such aspects. And if you think about the wheeled robot, maybe, then how we teach the base, basically, I think that would be also maybe question. So often maybe people want to just hold robot arm and then tries to let's go together or whatsoever, but then it's not, the human intention was not really tries to show end effector motion, but it was the intention of the human demonstrator was maybe tries to move a whole body part to the somewhere else, right? So distinguishing that and the where to contact, what is the really intuitive way of for the human users, and also how that can be really well understood by the robotic system. I think that would be important aspect maybe to consider in the future, I guess. Yeah.
Okay, thanks. Very interesting, actually, yes. So maybe if there is one more question, maybe we have time for one more, or if there is no more question, maybe we can go. Oh, Arash, yes, go ahead.
I tried to avoid it, but it was too hard not to ask this question. Very nice presentation, thank you. So actually, Francesco that asked questions, we are starting with him to look into learning from demonstration scenarios by looking into, let's say, not a classical way of doing this, some different ways of doing this. Our main question so far has been, of course, learning kinematics is quite straightforward. Even if when you're showing things and basically perceiving things. But when it comes to problem of dynamics, interaction forces, stiffness regulations and stuff, that the problem becomes really, really complicated, especially when it comes to industrial applications. I think one of the problems of kinesthetic teaching is when the complexity of the task raises, then therefore you need to include some insights about task dynamics. I was wondering, how would you comment on this? Like, what are the current state-of-the-art techniques to be able to also transfer those data? Because of course, from one hand, we lack sensory information. We cannot measure everything when it comes, especially to in-hand manipulation or interaction, continuous interaction. So, are there any, let's say, hybrid approaches that we learn something and we merge it with some theory, and we eventually are able to perform and learn and make the robot perform such complex tasks?
Yeah, that's a very nice question. I don't know the answer. So it's especially if you want to go to the more real world, right, industry setting. So you have to come up with somehow settings are simplified, but then you cannot really teach so nicely complex dexterous tasks also, right? Sometimes you are, in dilemma where you are, right? So we try to remove a lot of vision sensor and only work with joint torque sensing techniques or force torque sensors on the end effector, so that at least we do not rely on the very much difficult motion capture system is gone at least. So we can really work with only proprioceptive data, which is a kind of reliable in the industry setting. But then how much can we really teach precise tasks, right? So that is one of the things question. So we are looking into the more contact related tasks also. So tries to look at it. It's not only contact or non-contact task, but we try to see, is it like just like touch, or is it press? Is it about the inserting? Is it about the push, or push and slide while you are pushing some constraint in the downwards, right? So there are a lot of things, and then we try to look it into the robotics perspective or control perspective. What are the same in terms of constraints? And then these our set of proposed context skills are understandable by the users, or is it understandable by the robotic system, or what could be the main or desire the basic set of content related tasks. So we're looking in a lot on these kind of things at the moment. Yeah, and then we'll see how much it can go. It can go, and then I don't know how much extra things we can teach so nicely at the moment. So we are happy at the moment, of course, not only doing the kind of memory and saving and doing it, but also we try to go more, right? Also online teaching and augmenting skills. Whenever the new work cell comes, can we still use the existing knowledge and then expanding on time? We try to give a bit more bidirectional interaction between the robot is showing what it knows and what it can detect. It is something it seems to be wrong, and then it asks a human to correct, and human has this. So we want to try to see this bidirectional interaction between robot and user, so that we can learn fast, and then it can be more intuitive to the users. So we do also a bit of user studies about this new the collaborative robot programming we call, which is kind of combination of the robot learning and robot programming. But we try to see how really intuitive this is to the users. So we have to do, I think we have to consider different aspects, right? One thing is the complexity of the task, how much we can go for it, how intuitive it is, right? How much really simplify sensory systems so that we can be really applicable in the real world. Let's see how much we can go together.
Okay, good luck with that. Thank you very much.
Thank you.
Okay, thank you a lot, Tanguy. Very interesting talk and very interesting discussion. So if there are no more questions, maybe we can go to the next speaker. And also, as I said before, if you have some question, maybe at the end we can still talk a little bit more. So the next talk was given by Professor Jesus Gomez de Gabriel from the University of Malaga, and the title of this talk is floating platforms and physical human robot interaction and effector considerations. So in his talk, Jesus arises the problem of safe interaction in physical assisted device, and he also said that one of the let's say less tackle approaches is the direct physical contact between robots and humans. So as all of you probably know, the traditional approach is to try to avoid this contact. So he presented some approaches. One of them is a smart. I don't know why this is not okay. Yes, a smart detachable bracelet, as you can see in this picture, and its application to rescue and indoor robotics. He also told that one of the problems for this direct physical interaction between human and robots is the modeling of the human. So some of these approaches are based on LiDAR for in some industry applications, the use of vision-based sensor like open pose, this kind of strategies, and also based on haptic information, which is one of the approaches that he presented. So he also presented one word. This one that you are seeing right now is about haptic-based identification of human arm parameters. He also presented an underactuated gripper they developed at the University of Malaga based on proprioceptive and some words about proprioceptive-based grasping angle estimation, passive compliance for estimation, I mean, in terms of human-robot interaction. And He also presented this new family of gripper, which are called rolling fingers gripper. And the idea is or the goal is to reduce the number of actuators through the design of, let's say, new familiar of grippers for platform optimization. So there are, he presented that there are several approaches for this kind of problem, which are using very complex hands, using variable friction hands, and using active surfaces hands. And let's say another kind of solution is the one they propose, which is this rolling fingers gripper. So based on these talks, these are the discussion topics. So again, as for all of the speakers, the same questions, which is how far is this application to be integrated in an industrial application, and what challenges are yet to be solved. And also one thing probably is related to Jeon Park talk is the integration of these rolling finger hands for industrial application, which in my opinion can be very interesting for assembly application. And also another topic we could discuss about is say physical human robot interaction in manufacturing and logistic application, let's say from the point of view of the gripper design. So I would like to give you, let's say, the turn. So if Jesus, you want to add something, or if there are some questions from the audience, please go ahead.
Thank you very much, Juanma. Thank you for this nice introduction. Our contribution here is a set of small contributions about the physical interaction between the robot and the human, where the robot is taking the initiative of the contact. This is a different approach to most of the existing approaches, because here is the robot that approaches the human and grab the human, generally by the upper limbs. In our contribution, we presented some progressive contribution, and we started with indirect physical human interaction by designing the devices that can be automatically placed on human limbs. But this is one of the devices that, according to the first question, can be integrated in a real commercial application, because we can use this kind of indirect contact device to deploy devices not only on humans, but also in any kind of industrial environments, natural environment, using traffic lights or any kind of location where the breast can be attached. So we can use drones and other devices, other floating platform devices to attach this kind of devices. Also, we have been modeling the position of the human and also the contact forces by designing new kind of grippers. And finally, according to the words that Professor Park in his presentation said about the 3 levels of motion control in floating-based platform, we are focusing on the last one, on the gripper level motion control. So we are trying to keep away from the humanoid design and providing this new kind of grippers with additional degrees of freedom in order to perform in-hand manipulation. This is not human-like, but it provides new capabilities that could help in application like assembly, by reducing the number not only of gripper, but more important, the number of manipulator needed in this application. So if you are having a dual arm mobile platform, you can have a single arm mobile platform performing the same operation with a single gripper. This is our goal, and we are starting to develop real application of the grippers with in-hand manipulation capabilities.
Okay, thanks, Jesus. So I guess there are some. I think there are some questions. So Emir, please go ahead.
Okay, sure. Thank you very much, first of all, for your presentation. I have a question about passive gripper that you presented for the force estimation. So as far as I understand, you are using compression springs and with encoders to estimate the force, which is basically a series elastic actuation principle. What was the force result? What was the force accuracy and resolution, and I was wondering how repeatable it was in your experiments. Like,
let me see the results. I don't know if I can put a slide here, but there is. Let me see. And,
maybe you can share the screen if you.
Can I share the screen? Yeah.
Yes.
Here. Okay, this is the passive gripper. It's a underactuated gripper, and we add joint sensors to the passive joints,
yes.
so we can estimate the length of the compression of the spring. And this is a kinematic problem that we can solve, and we can have a lot of fair enough. It's not a precision device, but you can see here the differences between the ground truth in the measurement of the interaction force. This is lateral forces. And here you can see the difference between the compression force in this case, in the horizontal forces between a sensor we place inside the gripper and the estimated forces.
Okay.
It's I think it's fair enough.
Yes. Okay, I understand. And another question was about modeling the human arm. You put a kind of sensor here, and then you say that you considered anthropomorphic dimensions of the human to model the arm. I was wondering the equation, which equation that you used, like because I couldn't see in the presentation. Maybe
yes.
a bit detail, but just.
Okay, let me show you the.
Yeah.
Okay. We use two methods. We did experimental methods with Hawk transform and least square methods. We use both, and we compare the results of both methods. Okay, so here I can show you here the reference of this. Here. Wait, sorry. Here it is the reference to this work.
Jesus, we are not seeing the screen now.
Sorry. Sorry. Let me show you. Are you seeing my?
No.
No.
Yes.
Something
no.
is some. Okay. This is the reference here. Ruiz 2021. No. Yes, this is the one, and those are the. Here, those are the methods that we use, which are the Hawk transform and the least squares. So if you have some additional question, you can send us an email and we can discuss this.
Okay.
More.
Thank you for your answer.
Welcome.
Okay, so I don't know if
I have a quick question.
Okay, please go ahead.
So thank you very much for a nice presentation. I especially liked the last one, the rolling fingers. So I think that the design and the functionality must be very nice. I have one question for that. So it seems like it's very effective for round shape objects to manipulate. How about if you try to manipulate with objects not that round? It's very, I don't know how to say, like cube. Is it still going to work very well? Have you ever tried?
Okay, the goal of this design was to manipulate human limbs. So we didn't thought especially in manipulating hard square objects,
Yeah.
but this is something we want to test from now on, because we just made this design, and we want to test this with a new surface coating to make a better grip of the surface of the fingers. And probably this will be published soon if we have success.
Okay, thank you.
Okay, so I think we can go to the next talk. So thanks Jesus for your presentation and for this interesting discussion. And again, so first let me share my screen. Okay, can you see my screen now?
Yeah.
Okay, so let's go to the next presentation. So the next talk was given by John Ueda and Michael Libretto from the Georgia Tech. And the title of this talk is Posture-Dependent Robot Stabilization of Flexible-Based Manipulators. So in this summary, please excuse me because I am not an expert on this topic, so I will try my best to explain what you propose in this talk. If you have some other let's say thoughts or you want to add something, or maybe if I did any kind of mistake, please correct me. So in their talk, they present some control theory methods for manipulator with flexible basis. So the goal is to try to find a control method to control the endpoint of a robot with a flexible base. So one of the statements that the couple dynamics between rigid arm and flexible base are posture dependent. So they try to answer this question, which are how to optimally set a posture, and are these flexible robots stable with simple control strategies, and how can we treat flexible robots as rigid robots? So in this regards, they presented an approach to evaluate a posture-dependent robot stability of a linearized model about the endpoint. So they describe this normalized compriming factor and robust arm configuration concepts. And the goal is to try to find an analytical solution of the NCF margin for specific cases. Basically, the outcomes of this work is that it is possible to select a posture to achieve passivity for all flexible modes. And regarding the NCF margin, with the simultaneous diagonalization, the NCF stability margin for the aggregate system is equal to the lower NCF for each of the SISO subsystems. So basically, these were the let's say the outcomes of their work. So regarding the discussion topic, probably because I am not very expert on this, I mean, it was quite hard to me. So probably you want to add another, let's say, discussion points. But so still, there is the first question that maybe in this case, as this is a more theoretical, let's say, contribution, doesn't make more sense. But in any way, if you want to share, let's say, some comments on this respect. So the discussion topics are this. So the same question for everyone, which are how far are we to integrate this in a commercial application? What are the challenges? Also, one other discussion topic is the theoretical control models for robots with flexible bases and the real applications. So again, if probably you want to add something. So if Michael or John, you are here and you want to ask or sorry to ask to tell something, to add some comments, or if there are any questions from the audience, please go ahead.
Thank you for that introduction. As far as your first discussion point goes, the real application of this work is actually very doable at this point. The normalized coprime factor stability margin is incredibly common in the realm of H-infinity control. So as long as you can describe the system workspace in terms of that metric, you should be able to maximize your passivity and I guess similarly your normalized coprime factor stability, dissipativeness, for particular postures in the workspace within the neighborhood of your desired, I guess, control task. So the theoretical control models, the goal of the work was to be able to use simple endpoint feedback to avoid having to do heavy modeling on our flexible bases. And similar work has been done to consider robots with flexibilities in links and flexibilities in joints. However, the analytical solution of flexible robot structures has yet to be completed. That is forthcoming should we be able to solve the necessary Riccati equations. And real applications can be seen, I guess, anywhere you might have compliance in your base that you aren't really sure of. We did, I guess, in simulation applications of this work to a remote excavation system that had unmodeled flexibilities in its base between the upper, I guess, analogous manipulator section and the lower tracked base of the construction equipment.
Okay, thank you. So, are there any questions? So, okay, so actually I have one question. All these, let's say, methods regards the flexible bases, you also commented that it can be used for robots with, let's say, flexible joints, this kind of stuff. So in this, let's say, one of the main goals, let's say, or the main, let's say, goals of this, the use of these flexible robots is to provide a safe interaction with the so with the environment, with the human, this kind of stuff. So with this kind of method, how is for example in the case that we have something like the soft link, the soft robot that Concha showed before, interacting with the environment, how this interaction is model can be controlled, and also what if the environment which is interacting with the robot is also, let's say, flexible or is not, let's say, completely rigid, this kind of stuff.
Sure. So with regards to the soft robot presented earlier in the talk, that I guess the application of this material to soft robotics, I guess within the scope of safety, has not yet been considered. This was more in terms of disturbance rejection that arise from our unmodeled flexibilities in the system. I imagine that this metric can be used in an opposite way, as opposed to wanting dissipativeness, I guess, so as to avoid oscillation. One might be able to use this metric in terms of susceptibility of certain postures to bending. I have not yet looked at that, so I can't say for sure one way or another. As for your second question, in terms of I believe it was flexibility at the endpoint, at contact points, rather. Correct me if I'm wrong.
Yes, like for example, if the robot is touching a surface and this surface is not rigid, how this, let's say, can affect the controller, the model, etc.
Right. Okay. As far as I'm aware we should be able to include that as another flexibility in the system. All of the flexibilities were treated as discrete viscoelastic elements within the dynamic system. I have not yet looked at what would happen, I guess, should our open kinematic chain become a closed kinematic chain with flexibilities on both ends. But if we are working with a floating base robot that is, I'm going to say, rigidly attached to a compliant system, that would present itself, in my opinion, the same way, but inverted, whereas the original concept was the attachment of our floating base to a flexible system. We can treat the flexible system as the base and the floating base as our free endpoint. Again, I would have to look at the dynamics and how they take shape and what structural properties we may be able to lend in that situation.
Okay, thank you. Are there any other questions? Or any other comments you want to add, Michael or John or something?
I think I'm good. Thank you very much.
Okay, thank you very much for your presentation. It was very interesting, especially for me that I didn't have to, let's say, this background on this kind of topics. So thank you. So probably we are actually running out of time, so we can go to the next talk, which actually was my talk. So let me introduce myself again. So I'm Juanma from the Istituto Italiano di Tecnologia, and I presented this talk entitled Active Supernumerary Bodies for Physical Robotic Assistance in Industrial Operations. So, okay, let me share with you this video in which my colleague Wansu presented a couple of years ago this Mokaman concept. So the idea of this Mokaman is let's say to put together the benefits of using supernumerary limbs and cobots. So the idea here is that the idea behind this concept is that you can have a mobile manipulator and an attached, let's say, physical interface, which you can use to attach to the robot to do some kind of local manipulation task. So one of the problems of these interfaces presented before is that it uses, let's say, non-industrial like design, because it required an EMG sensor to try to estimate what were the commands from the human to the robot, and also it included and let's say an magnetic clamp so that the human can attach to the robot, try to, let's say, with a force torque sensor and admittance controller to command the robot, let's say, locally. So from this problem, we designed a new, let's say, industrial-like interface, which is the one that you are seeing in the video. Is basically a handler with a force torque sensor and a buttons board, which the human can directly grasp to carry out some kind of, let's say, local operation task. And with these buttons, the human can, let's say, the worker can command different stuff to the robot, like to change from, let's say, more priority locomotion to more priority manipulation, this kind of stuff. Along with this, we also presented some the whole body impedance controller of this kind of robot, which includes torque control robotic arm. So one of the, let's say, drawbacks of this platform is that with the use of torque control robots, we don't have too much high payload, which is a requirement for, let's say, many industrial applications. So in this other work, we present the use of this mobile manipulator, which is based on the previous concept. That's in this one, we are using a universal robot UR16, which have let's say a higher payload. So in this case, we presented this, the controller of this robot, the whole body controller is a little bit different than the one presented before, because with this one, as the robot doesn't have the torque sensor on the joints, we couldn't, let's say, include this impedance behavior. So what we have is this admittance interface with admittance controller based on the force exerted by the human, and this velocity-based whole body controller. We developed some tests of this robot for this overhead drilling task, which is let's say very common in industrial applications. And we are right now carrying out some usability studies, try to understand what is the user acceptability of this kind of technology. So from this talk, I would like to raise some, let's say again, some discussion topics. So again, how far is the solution for this industrial for industrial application? What challenges are yet to be solved? Other topics are the use of supernumerary bodies in industrial scenarios. One things that we are planning to, let's say, to improve in future works is to enhance this physical assistance, because right now the robot is just giving some, let's say, some compensation of the weight of the object, but that doesn't include any advanced physical assistance. And also we want to go forward on the design of new advanced interfaces. And regarding the use of interfaces, I will also retake the question I wanted to ask to Dongyi Lee, which is how can we exploit this kind of system with these interfaces, or maybe more advanced one that can have, let's say, more or different human-robot communication in order to, let's say, to apply this for learning techniques. And also, if anyone have any question, please feel free to ask.
Yeah, so it's a very nice work actually, what you presented, and I liked it a lot, and maybe we could work together in the future. I have some idea. Okay, but let's see. This supernumerary body, right, physically attaching to the human, right, it can be give you extra, right, the power, superpower to the human, but also it can constrain the human's movements as well, right? So how sometimes if I see some movies, it looks like very uncomfortable to the human users, but sometimes I can really see it really assist, right, the loading, the heavy objects you're lifting and so on. So also question to you, what would be, good way we can balance out those two side effects, or these two, sides? What would be our philosophy to do the designing?
Yeah, thank you for your question. Yeah, actually, one of the motivation of this work was the related to the, let's say, to the motion constraint that the robots provides to the humans. So actually, the point is that the, let's say, most physical assisted devices in industry like exoskeletons or supernumerary limbs constrains the motion of the work, especially exoskeleton, because they don't have all the degrees of freedom that let's say, the same number of degrees of freedom as the human. So if you want to apply to the worker wants to, let's say, to move some kind of this kind of the degrees of freedom that the exoskeleton is not included, probably you cannot. So one of the motivation is that, okay, let's use these supernumerary limbs. So basically the traditional supernumerary limbs are attached to the body, and then you can use this kind of limbs to let's say to increase your, let's say, capabilities, your physical capabilities. But there are, let's say, two main drawbacks. The first one is that you have to carry this all this weight, so you are not carrying the weight of the object that you are manipulating, but you have to carry all the extra weight of these limbs. And the other problem is that this kind of I mean the current supernumerary limbs doesn't have too much power for this high payload application. So based on these two, let's say two points, we thought of using this kind of cobot as a supernumerary. It's not a supernumerary limb; it's more like a supernumerary body that you can use as a tool. So it's something that if you need to do a specific task in a certain moment that requires some, let's say, high payload, or maybe if you do a repetitive task with I don't know, maybe even a 2 kilogram object, if you have to do some repetitive tasks with this kind of object, with this kind of tool, it can let's say ends with some kind of musculoskeletal disorder. So that was the motivation. So yeah, actually regarding the design, the thing is that as we are using this kind of cobot, and as probably you can see in the video, in this one. So as you can see here, yeah, there still are some constraints on the human motion, but I will say that most of them come from the task itself. So the human is constrained, but if the human has to do this task without the robot, probably the constraints will be the same. So all this motion constraint came, let's say, from the task. Of course, there is this, let's say, safety concerns regarding the distance from the base to the human, this kind of stuff that we have to consider. But apart from that, yeah, I will say is also in this usability study we are carrying out, we are considering this kind of factor, asking the users if they felt comfortable during the task, if there were some kind of let's say inconvenient and uncomfortable, this kind of thing. And regarding the yeah, sure.
Sorry.
No, go ahead.
No, so yeah, this is actually an ongoing study. This was a continuation of what we started with Mansuki and the initial work of Wokam. And with Juanma, we are also looking into this question that you asked. We actually ran some studies on 10 subjects, and this is unpublished work. We are working on it now. So how this human movement patterns look with and without using this system, and we would be really interested in using also other systems like exoskeletons, whole body exoskeletons, of course, if we will find some to see the differences and how these constraints are being. So the preliminary results show that there's, as Juanma was mentioning, there's very little difference between what the person is doing with and without the, let's say, the supernumerary body. And this suggests that these systems impose minimum constraints, and people can perform their jobs, of course, more ergonomically, but more naturally, as if they were doing it without such assistive systems.
If I may, can I have one more question? So what would be your ideal system setting? What kind of sensor do you want to have it or not? Do you want to have a force torque sensor at the end? Or do you think an EMG sensor would be really enough? What would be your ideal choice? What do you want to have it in the future?
Yeah, okay. So yeah, actually the EMG sensor at the beginning, we were using it to command different, let's say, to send different commands to the robot. In the end, we are using this EMG sensor only to measure the muscular activity of the worker, to see how is this reduction when you are using the robot or when you are not using, and to, let's say, to move the robot, we are just using a force torque sensor, which is included in the interface itself, and without, I mean, with an admittance controller, we are just mapping the forces exerted by the human into the desired velocities to the robot. But actually, one of the points we were also thinking about is that these force torque sensors are really expensive. So if we think about real industrial application, one of the let's say most important point is how to reduce the cost. One of the things that we are thinking, how can we let's say use different kind of let's say sensor, different kind of approach, try to avoid to use this let's say expensive force torque sensor. I don't know if that answers your question or.
Yeah, do you have an idea how to remove it?
No, actually, we were thinking. No, there are some applications like the 3D mouses. So maybe we were thinking of using something similar, but I mean, it was just an idea. We don't really know. Okay, I think also Wansu has some questions. So Wansu, please go ahead.
No, actually, it's not the question. Actually, to be clear, at the beginning, the use of the EMG is for just to recognize some mode, to change the mode between the locomotion or manipulation, something like that. So here we're not using the EMG sensor for measuring the human force. But force torque sensors, yeah, at the beginning, we thought it's very necessary to measure the human interaction forces to control the robots, such as for using the but in some idea, we can also try to attach some algorithm from the exoskeleton things without using the force torque sensor. Somehow, we can also consider to methods such as disturbance observer, which already have been implemented in the exoskeleton system to estimate the interaction forces to control the robots instead of using the force sensor, maybe.
So the first, we can hear you with a very low voice. I don't know if it's me, Wansu, or everybody else. But the first part, what Wansu was trying to say is for the EMGs, we only use for the classification of the movements, if it's arm, base, or both of them. So for the rest, it was quite obvious, and this voice was better. Yeah.
Maybe it's my fault.
No, if you could please speak a bit louder.
Yes. Do you hear me well, or?
Now, yes, much better.
Okay. No, I was saying that maybe we can also consider to using another control method, such as the disturbance observer, to measure the interaction torques instead of the measuring the interaction forces from the force torque sensor, but we can just estimate the interaction forces using another dynamics model of the mockup. So what I'm using in the method to control the exoskeleton, moving exoskeleton, that time I just using this disturbance observer techniques to estimate the interaction forces to control the low body exoskeleton with the habitable object. And there are so many ways to also to control the robots without using the force.
Yeah, so Wansu, if I can add something, so yeah, actually, this is one of the points is that how using this disturbance observer, how can we distinguish between the interaction, let's say, between the human and the robot and the with the environment? Wansu?
We cannot hear him, I guess.
No, maybe
some connection problem.
Yeah.
Okay.
So
Yeah.
anyway, we can talk with Wansu later, no problem. So I guess if no one else have any other question, maybe if someone has one question from another speaker from a previous talk, we can have some time now. So please, if you have any question, not only to me but to other speaker, please go ahead. And
I would have one more for Juanma.
yeah, of course.
What's your experience with regard to actual contact, for example, for this drilling task, like actual contact in the context of admittance control? Is there any stability issues you witness?
Yeah, actually, when we were doing this experiment, of course, if there are some constant there can be some instability, let's say, problem. Also, we were testing different kind of let's say admittance controller methods. Try to look at this kind of problem. So, for example, using just a constant admittance controller, one of the problem was the rigidity, let's say the rigidity of the arm of the human. So if the arm of the human is more rigid, and then tries to apply some, let's say, some motions, apply some forces, this will, yeah, of course, become some, let's say, the system will become unstable. So one of the we are proposing, we are, let's say, applying different kind of methods like variable admittance controllers, trying to vary it also the damping, the stiffness, let's say the admittance, the admittance behavior. Also, we are related to conscious talk. We are also trying to apply some kind of fractional order controllers for this kind of stuff. But yeah, these are the kind of things we are still studying about this problem.
Yeah. Thanks.
Thank you. If you have some insight that you want to share, of course, we will be
I don't have
very
any.
okay. Thank you.
I'm just curious because I'm purely impedance. Like my research is purely on impedance, and I don't have any experience with admittance controls.
Okay, thanks.
Johannes, I think the biggest problem about admittance control, as you anticipated, is when you have high gains, of course, at the contact level. But with low gains, usually you don't have those issues. So it's a matter of tuning. But of course, the problem that you mentioned, the instability, there are several techniques to look into. As you know, the energy tank, energy observers and stuff. I don't know, this adds more to the complexity of the problem than resolving it. So maybe also there are some fractional order admittance controllers that look into this, different damping ratios for different, they set different damping and stiffness to different, let's say, action reaction, let's say position force, let's say different frequency, let's say interactions. It's a very interesting topic to work on, and we are very open to discussions, collaborations, if anybody wants to, especially the topic of learning from the human demonstrations, or at this point, how to ensure smoothness of the contact. Of course, this would be a great opportunity to join forces, and one of the objectives of this workshop is this one, of course.
How about, sorry, one more question. How about safety regarding like collision with the environment, and or also like clamping a human? Like, I don't know. I mean, it's kind of obvious that you don't want to get into the tool, right? But like, let's say the robot colliding with the environment first. So maybe let's assume you want to drill somewhere, but right next to it there's like, it's so rigid that the robot, like if you keep pushing, like if the human operator keeps pushing, the robot just needs to brake, or the, I don't know, the object breaks or something breaks. You see what I mean? Like if the human is pushing towards the drill or the drilling location, and basically the robot just drives into this rigid wall with like rigidly.
Yeah, I mean, these kind of things right now can happen. So the let's say all the security level on this regard, I mean, on this respect regards to the human, let's say, but also, I mean, for the case of the Franca arm, as we said, we have this impedance, let's say, behavior. So it's kind of, let's say, intrinsically safety, like this. And in the case of the universal robot, this is the let's say, velocity-based control. So in this case, we don't have this impedance behavior. Let's say the security level that this robot integrates at the moment to consider it collaborative is that if it detects an external collision, it will stop. That's let's say an external unexpected collision. Let's say.
Yeah.
So that's
Sorry, Juanma, for the sake of clarity, so there are two, actually the robot itself is always running an impedance control. The only admittance filter is the point of interaction that comes with the human. So where you see the Juanma is holding the hand, which was also the same initial work with Wansu, there's another additional four-stroke sensor, which basically decouples the interaction forces applied by the human and the interaction forces that are applied from the environment. So essentially this admittance filter is just creates some let's say desired trajectories that adds to the impedance controller of the robot, which runs at the end it runs an impedance controller, right?
Okay.
So in the end it's impedance control, it's position, let's call it within the processes, and it's safe, and it runs all the safety let's say stuff. And then recently, of course, we also integrated some hierarchical optimization that basically it also helps the mobile platform to stay a bit away from the person and while avoiding also static obstacles at the environment. Sorry, Juanma, to interrupt. I just wanted to make sure that these two ports of interaction are.
That's a really good point. Thanks.
Sorry. Yeah, thank you, Ash. Thank you, Ash.
That's cool.
Okay, so are there any other questions, any other comments, any other thing you want to share with me, with other speaker, whatever?
So my general question to you, how do you like this format? Because we are new to this world of virtual, so we are trying out this. I think this Juanma's idea was quite nice, you know, and I still like the live presentations, but this year Humanoids constrained us to have only 2 hours of live session, and we thought maybe Juanma suggested this could be the best instead of going through the presentations and stuff. I think it was really good, in my opinion. A lot of nice discussions came up, and all thanks to Juanma and his really nice organization, and the speakers, of course.
I think you did a great job. So thank you very much for organizing. Sometimes, of course, I like to give more live talks, but also pre-recording takes more time. But still, you know, with a limited time, having interactive discussion is more important than only listening to talks. So I think it was a great choice. So, and then thank you very much.
Yeah, thank you very much. The same from my side. I think it has been the best way possible. So congratulations on the organization, and thank you for inviting us to this chat. I think it has been very, very, very interesting. Thank you.
Okay, thank you everyone. So in my opinion, let's say the only good point of having this virtual, let's say, workshop, virtual meetings, that we can have all the recorded talks on the website, let's say, on the internet forever. So this is the only, let's say, in my opinion, positive point. So I hope on the next conferences we can meet again in person. We can have another kind of interactive discussion also. And thank you all. Thank you all of the organizers, and thank you all of the speakers for all this interactive discussion, for the super interesting, say, talks. And as I said, hope to see you soon.
Okay.
So
Thank you again. Yeah.
I guess we can conclude the workshop.
Bye,
Thanks.
everyone.
Thanks a lot.
Thanks a lot.
Have a nice day.
Thank you.
Interesting
Bye.
conference.
Bye bye.
Thanks so much.
Bye.